Oh, thanks for coming. For years, we've been working on a new programming language called Verse. Verse is motivated by the needs of the metaverse, which is this emerging medium you've heard about in science fiction literature like Snow Crash. It tells us a lot of crazy things about this new idea, but in short, the metaverse is social entertainment. It's people going into Fortnite and not just playing a game, but hanging out together with friends, talking to each other, going around and exploring this world and having fun. And most critically, it's about having millions of creators empowered to build content in this world together. And so the metaverse isn't about one company's creation, it's about millions of programmers and artists, each contributing to build this new shared environment. And this is very much unlike all of the other software platforms we're used to today. Yeah, we're used to app platforms where you're running one app at a time that's built by one company, and it has a static code base that's compiled once, deployed, and it doesn't change until they update it. Whereas the metaverse is a much more interesting usage case. It's a continuous, seamless world that starts up and continually evolves over time. Different programmers can be updating different parts of it, both code and content. And so what we need here is a living, breathing code ecosystem in which code can evolve without breaking backwards compatibility over very long periods of time. And that imposes some really unique requirements in a programming language. And so we've really been thinking a lot about what we need here. We need something that's really easy to use, because a lot of the people who are going to be programming for this new medium are going to be learning programming for the first time. So we can't assume they know C++ and all of these other languages. We need something that anybody can learn. I learned on BASIC. A lot of people today learn on JavaScript. Some people learn on Haskell. But we really aspire to build something that's easy enough and familiar enough that people can really easily get acclimated to it. We also need a foundation that's very robust, because when you're building code live that can be used by millions of users playing together, you really want to catch problems before they occur, before you ship your code, and have a very robust compile time toolkit for that. And so static verification of code is more important than ever before. And especially in the case where you have millions of modules built by different people, where each module has to be type checked for backwards compatibility with previous versions of it to ensure that it doesn't break anything else in the entire world, is a really critical part. We're also thinking we want a single live metaverse that can operate without limitations. In Fortnite Battle Royale, you're in a 100-player island. You all drop down and fight, and one comes out as the winner. And the reason Fortnite is 100 players is because we don't have the technology to scale up to support millions of players in a single session. Though at peak there have been more than 20 million Fortnite players playing Fortnite in the world, they're not all in the same space. But in the future, we want to correct that. We want to put everybody together into one massive shared simulation where the logic for the simulation is just expressed in code. We're not talking about code that sends network message to database servers and coordinates all of these asynchronous microservices. We're talking about just code. And so the hope for this metaverse is that it's actually running on what looks like a single infinitely fast machine that runs single-threaded code the ordinary way, that the machine never shuts down, and so you have automatic data persistence. Your simulation just keeps running. And as modules are updated backwards compatibly, they just resume running along the code paths that they've been in previously. So there's some really lofty ambitions here. And so we built Verse as an attempt to do this. Verse is not a terrifically complicated language. Here we're seeing the BNF grammar. It doesn't fit very well on this screen, but it's not crazy, and it's relatively well specified. Essentially, it's a strongly typed language with compile time guarantees. It's in the Pascal, TypeScript, C# family of languages. So there are curly braces, but there's also significant indentation. And the syntax is really intended to be broadly learnable by anybody. It allows The paradigm we're trying to use here is functional logic. And I'll talk a lot more about why functional logic is interesting later on. But the aim is to enable all the power of programming in a language like Haskell, instead of lazy evaluation, we have something called lenient evaluation, which still enables you to run code out of order in order to access things as you're defining them and build these really impressive recursive definitions that don't require side effects unnecessarily, as happens in imperative languages. So the idea is we want to enable people to keep within the pure functional subset of the language as much as possible and only use side effects when they really need to because they're mutating some global shared state. The language has an effect system instead of monads, and so that leads to some really interesting trade-offs. And we've also worked on some very interesting new approaches to program verification, which I'll talk about. And Verse is shipping today. We're really developing it from two ends simultaneously. First of all, in Fortnite, there's live today, there's a programming environment which we codename ShipVerse. It's a subset of the full verse semantics that we're talking about here. But it works. There's a compiler toolchain for it, and thousands of programmers are writing code for it right now. But at the same time, we're also maintaining the specification and ambition for what the ultimate language should be. We call that MaxVerse. And we're planning out denotational semantics, verification semantics, and all of the other details of it, so that as the language evolves, that we know what target we're aiming for, and we don't paint ourselves into a corner with new features as they come online. But here's what the language looks like. The intent is to be really simple and ordinary code for people. Here we have a loop that just goes through and prints even numbers. It's going to go through a range of numbers, ask if each one divided by 2 is a natural number. If that's true, then it's even. And that captures a really interesting point. Verse math is actual math. The integers are actual mathematical integers. There's not like this magic overflow. When you divide integers by integers, you get rational numbers. And the aim is to follow math as closely as possible so that there's not another barrier of people who've learned arithmetic in school then needing to go in and learn programming language arithmetic. And here's a quick look at the syntax. The aim is to be really mainstream. You see we have colons for type definitions in the TypeScript or Pascal family. And also to be multi-paradigm. You see here programming constructs from ordinary languages. There's also functional logic constructs, and there's even markup. Because we want to be able to express all of these different programming paradigms without moving between different languages. But the really interesting decision we've made is to dig into functional logic as a programming paradigm. Now, this always scares people when you talk about functional logic, because we have all encountered like Prolog and other of the functional logic and pure logic languages, and they're always really, really strange, right? You have this notion of backtracking and non-deterministic evaluation and horn clauses and resolution. But that's not what we're really doing here in Verse. What we're really doing is saying that we're providing an ordinary programming language that looks like ordinary programming languages look, except we have added and generalized some features that work within conditionals and within loops that enable you to use functional logic features to do more powerful and safer conditionals and do more powerful and more expressive loops. And this really goes towards Worth's maxim, which is power through simplicity and simplicity through generality. We don't want to write a huge number of features. We want to provide a very small number of features that you can combine together as powerfully as possible. If we look at the history of programming languages so far, we see everybody has implemented some amount of functional logic as ad hoc features in their language. What is functional logic about? It's about running program code that has two additional features. One is your code can fail at any time, and failure in a conditional, like if you're writing an if statement and then you encounter some code that fails, failure just means let's immediately jump out of the if statement and go into the else branch. And if you run the entire span of code in the conditional without failing, you succeed. and you go to the then branch of the conditional. Right, and so we're really talking about control flow with this feature set. And similarly, there's another feature in functional logic, which is multiple value production, which is in a for loop. What you're really doing in a traditional imperative language is iterating through a set of values and then running some logic based on them. But in functional logic, there's just a little bit more of a general feature set for expressing that. In a for loop, you have multiple value producing statements, like let's go through all of the elements of this array, or let's go through these consecutive integers, or some other query like that. And very much like Haskell list comprehensions and other programming language features, you have the ability to produce multiple values in a very composable way. And so here's what it really looks like in practice. In traditional programming languages, you have a bunch of Boolean operators, and some of them short circuit. If you have an AND statement and the first argument fails, you skip the second one. If you have an OR statement and the first argument succeeds, you skip the second one. Those are control flow primitives, but they're kind of limited in scope and duration. Whereas in functional logic, we've sorted out the duration of the control flow a little bit more generally. So in an if statement, you're just asking, is this condition true? If it fails, you go to the then branch and so on. But the neat thing in the second example here in the middle is that in a condition, we can actually bind a variable. So when you go to inverse to access an array at a certain index, if the index is in the range of the array, you get its value and it succeeds. If it's out of the range, you fail. And so you can use a conditional test like this and then bind variables, and upon success, you can access these bound variables. We've all written a lot of loops and tests in other languages where we're asking, do these really complicated conditions hold? And then within the condition, we're doing a bunch of things that are only safe if those conditions hold. And it's a little bit fragile, right? If you remove some conditions or you forget to keep everything perfectly in sync, then you might be doing some really unsafe things in the body of the loop. And functional logic just enables you to write more robust code by having the compiler catch those cases and tell you, aha, that might fail there, so you're not allowed to do that. It's telling you that you haven't done the proper check. And so functional logic gives us more ways to statically verify that our programs are correct and safe than traditional languages. There's another interesting thing happening on the right, which is unification. We're starting out and saying, hey, there's this unknown integer, and depending on this condition, we'll fill it in with different values. This is pure functional code here, and that's kind of the mind-bending thing here. We're not talking about side effects of mutation. We're talking about taking unknown values and filling them in asynchronously as we go. And that's the core of logic languages, and it's the core of functional logic, but it means we can have much more expressive types of code without requiring side effects. Right? The more we can eliminate side effects from code, the more we can increase the code's predictability. And here's some example of iteration. It just looks like a Haskell list comprehension, but instead of using a list monad object to control traversal and processing of code, we're using functional logic to produce a set of values, filter them out through failure, and then execute some code on the right. And we've made all of these into first-class features. So the second function here is identifier. We're going to ask, is the string a programming language identifier? And this has a funny annotation on it, an effect annotation saying decides. That means this function may succeed or fail, and it's decidable at runtime. So you pass it a string, and is identifier succeeds or fails, and then let's break down its logic. It goes through all of the characters and asks if each one is some sort of alphanumeric character. But what it's really doing is it's taking each character in the array, it's unifying against this multi-valued expression. If it matches one of the things in the range, that succeeds. Then it's doing a disjunction, producing multiple values. And so this isn't like some crazy syntax that's breaking down into ordinary code. It's, the dot is an operator that produces a range of value. The vertical pipe is an operator that produces multiple values. Equality is a unification operator. The translation of all of these primitives is very simple in general. Here we have another loop to do a test of if a number is prime. But check out that at the bottom, the if statement containing a for loop. What we're doing here is, what are we doing? We're going through all of these numbers in the range j, and then we're asking if the thing is not a natural number. So on the one hand, we're combining iteration with a check. So we're saying if for all j's, this test on the right succeeds, in order to ask the thing is prime. It shows that these features are really compositional. And where you have a for loop, what you're really asking in a for loop is a universally quantified existential, or you're asking for all elements in this domain where these conditions hold, do these other conditions hold? And so you can write simpler code this way. In C++, you end up with a loop with a bunch of side variables you're mutating to keep track of whether you found the thing you're looking for. In Haskell, you often have to have a bunch of list comprehensions and some complicated combinators to move in and out of different monads, or denest, or ask if an entire array of booleans are all true, or if some are false. Whereas here, it's a little bit more pointful, right? You're just checking individual values, checking for success and failure, and moving on. And so, this is done just with a very small number of syntactic primitives, which are handled in a very general way. But the other thing about the language is, instead of dealing with effects through monads, we deal with effects through an effect system. You're right, and the idea here is, Haskell and Verse each are functional languages at the core that support side effects through other means, right? In Haskell, it's through monads, and you can have the IO monad at the top of your program. But in Verse, it sees effects annotations, which say what effects you're allowed to operate in. And if you want to compare it to Haskell, it's like we're plumbing the STM and IO and logic T-monad from the logic package through every program, and using the effect system to say which parts of the system we can turn off in local contexts, which give us more power of reasoning. And so there's this lattice of effects that your program can have. It encompasses both functional logic effects on the right, but also traditional effects on the left. And it really is an interesting breakdown of the kind of side effects a program can have, right? Because if you read and write memory but don't do anything irreversible, then you're in this transactional world. You could run code speculatively using transactional memory and get out. But we also have total functional programming as a subset of the effect system, so that you can write code that can be proof carrying, prove things about your programs when you're in this total functional programming subset, where your program is guaranteed not to diverge. And our goal, which we've not succeeded with yet, but are working on fiercely, is a transactional memory at the scale of a data center. Tens of thousands of machines collaborating together to simulate one world, in which the mutable state of everything in the world is accessible to any part of the program just through code, right? We're not talking about network message passing or other really complex shared memory protocols. Just transactions is the sole paradigm for sorting everything out. And I really believe that this technology's time is coming, and that over the next decade, this will become the primary way that we deal with concurrency in the future. Not proven, and it's far from proven, but I think this is coming. Another really interesting thing we're doing with Verse is instead of just type checking, we're doing full program verification as our long-term strategy here. This is a really big topic. You could spend a day on it in its own. But the idea is instead of just asking if every type in the program is correct and allowing many other categories of runtime errors through to cause your program to crash at runtime, in C#, there's null pointer exceptions, and uncaught exceptions thrown out of code, and all kinds of other things that can go wrong. In Verse, the aim is to statically verify that all control flow paths in your program don't lead to all of these sorts of runtime errors, so that your program is free of runtime errors, with a couple exceptions. First of all, if you want to crash your program by calling a runtime error function, you can do that. If your program wants to run away and infinitely loop, we can't catch that in the general case. But the idea is to search through the program using a really structured methodology to find all things that can go wrong. Because in functional logic, you don't just have to catch type mismatches. You have to also catch effects that may occur where they're not allowed. Like at the top level of your program, you're just writing code. It's not allowed to fail. So we have to verify that the functional logic failure effect is absent there. We've broken that down in some really interesting ways. One other really interesting property of verse is that it's a single level language. There's not a separate type system and value language, as is traditionally the case, but rather like a higher order function, a functor from types to types. It's just a function that takes types as parameters and returns types as a result. And if it's a pure function, then the verifier can reason about that in the equivalent ways to a traditional language with higher order type features. And it turns out that this is a really simplifying assumption. If you're having to commit to doing full program verification anyway, then you already need to do arbitrary evaluation of complex expressions and values at compile time, and have a really sophisticated system for sorting that out. And so you might as well build a language that's a single level, and then all of your value language features could become available at the type level. And this has some other really simplifying benefits to the language itself. And there's a query type system. You know, one of the things that's come out of dynamically typed programming languages like JavaScript is really successful attempts to add on top of them static type systems like TypeScript on top of JavaScript. And of course, they're restricted. Like, their type system has to just reason about the values of the language. And so we take a language where values are really the only primitive thing that we know about, and types are just constructs that characterize what values exist in the language. And so we're a lot closer to set theory from mathematics than we are to traditional type theory. A value doesn't have a type, just as the number 3 doesn't have a set it belongs to, right? 3 belongs to every set that contains 3. There are infinitely many of them, and we're okay with that. And this kind of restricts us in how we express our language, but that restriction turns out to be really empowering and enable some cool features. And so functional logic being the main topic here, we want to break this down and show that functional logic doesn't need to be this crazy, mysterious thing as we've often experienced it to be in Prolog and other languages. And so Simon Peyton Jones is going to talk about how we actually deal with functional logic at runtime.
Great. Thanks, Tim. Let me just switch presentations. Good. Is this great? All right. Oh, now, strange sound. Can you hear me okay? Good? Okay, start waving. I might switch microphones and see if it's any better. It's a pleasure to see you all. Happy 10th birthday, Lambda Days. This is, what I'm going to do is I'm going to take another sweep through the big vision that Tim has described, right? Because my job is to kind of reverse engineer out of Tim's head some of this big vision into a form that ordinary people can understand. So we're going to take a rather closer look at a little bit of verse, particularly the functional logic component, and try to give you a sense about how it works in a little bit more detail than he did. So verse 1 is just to say that the core of verse, as Tim was saying, is a perfectly ordinary functional language. It has values, numbers, strings, and so forth. And arrays, we call arrays and tuples in verse are the same thing, just a finite sequence of things. There's a in order to be able to write, they're usually written with round parentheses and commas, like in Haskell, but since you want to write a singleton array and an empty array, there's also this array keyword here. Okay, so then bindings, if you want to bring a variable into scope, these colon equals is very much like a let binding in Haskell, right? So it brings X into scope and it binds it to a particular right-hand side. And here, just like in a functional language with letrec, the order of these things doesn't matter. So in the last one, we can bind X after we bound Y, right? It's not just left to right. You can create bindings in any order. So far, so good. All right, I'm just going to whiz on because this part should be fairly straightforward. Lambdas, yes, it's Lambda Days, and you'll be unsurprised to hear that verse has lambda. It's written with an infix fat arrow rather than a backslash like it is in Haskell. And you can also write lambdas either in the bottom of the slide with an infix fat arrow, or with a more conventional, like you say f of x equals or f of pattern equals. You can write that. That's the sort of top half of the slide. Okay, it's all fairly conventional. I'm not going to go into too much detail here. Okay, and then putting all this together and adding conditionals, we just write an ordinary recursive factorial function. So far, so good. Okay. That's the sort of standard functional core. Should make you feel secure, I hope. which is a good thing because it may not last very long. Right, so now, so two things we're going to cover now, choice and functional logic. So first thing, choice. So in verse, in Haskell, every expression denotes a single value, right? So 3 plus 4 denotes 7. And every expression I evaluated to one value. But in verse, an expression can evaluate to one value, to 0 values, or to many values. So 3 evaluates to, well, just one value, denotes one value. 3 vertical bar 4, the choice between 3 or 4, produces 2 values. I say yields or produces or delivers 2 values. It's a bit like an iterator, right? And rather quirkily, false question mark is verse's way of spelling fail, meaning deliver 0 values. So fail in verse, or false question mark, is like nothing in Haskell, or the option, what would it be in Erlang? Must be a way of saying nothing. It's not a bad thing, right? Undefined. Oh, okay, undefined. It's not a crash, right? If in Haskell, if you called error blah, that means something terrible has gone wrong, stop the world, right? If you return nothing, that just means, well, I'm returning a value and it's called nothing and you can pattern match on it. It's a perfectly ordinary thing to happen. It's like false or something. So here, fail sounds drastic, but it's not. It's simply, this expression has returned no values, okay? And that's spelled false. And then the reverse notations for describing multiple values, right? So 1.10 is all the numbers between 1 and 10. Okay? So, and then you can bind variables to elements of this choice. So at this stage, verse is looking very much like as if Haskell's list comprehensions are sort of a fundamental part of the computational fabric, and that's not a bad way to think about it. So here in this expression, here what do we got? We got, wait. Is this going to work? Yes. Up here, I'm binding x to the choice of 1, 7, and 2, but I do not bind x to some kind of multiple value and then carry on. No, I bind x to 1, and then I execute everything that follows, and then I bind x to 2 and execute everything that follows, and then I bind x to 7 and then to 2. Does that make sense? So this expression will yield the values 2, 8, and 3. But at any moment, you might, just as in the Haskell list comprehension, which I've written here, x only gets a single, x has type int, not, multi-int. Okay? Good. Incidentally, if I say anything that isn't completely clear to you, please wave an arm, because we can talk during this. I'd much rather have questions during the talk, particularly because if you get lost, you're going to get very lost. Okay. So far, so good? Yeah. Oh, yes, Thomas.
So you make the choice after that you have done the computation.
You make the choice after you've done the computation.
You have a choice between 1, 7, and 2.
Yes, choice between 1, 7, and 2.
You add 1 to each of them, and then you make a choice.
No, you're saying, do I add 1 to each of them? I don't go through the choices and add 1 to each of them. Rather, just like in Haskell list comprehension, I draw x from the list 1, 7, 2, and then successively, each time I draw the first element, and I add 1 to that. I draw the second element, I add 1 to that. So you can think of it as like, well, a loop, a for loop. That's what a Haskell list comprehension. That's exactly what's going on here. Okay? Good. Yeah. Oh, can I add a nothing in between? Like, could I say 1 vertical bar fail false question mark vertical bar? Absolutely. And then it would still yield 1, 7, and 2, because the false question mark bit, the fail, yields no values. So if you have E1 choice E2, you get all the values from E1, followed by all the values from E2. And if there are no values from one of those expressions, well and good. Okay. Yeah.
Can I reflect back? So if I have an expression that can have multiple values, can I reflect it back into a sequence of values?
If I have an expression that yields multiple values, can I reflect it back into a single value? Yes, we're going to come to that. Very good, very insightful observation, an unusual feature of verse, yes.
You said successively.
Successively, yes.
Did you mean in sequence over
I
time?
did mean in sequence, so I'd be careful to say successively, because order is important. I'm going to come to that too. Yes, thanks. Yeah, you're asking all the right questions. Good.
Can you hear me?
Yes, I can hear you.
So you said we could add a false question mark somewhere
In that choice, 1 vertical bar, false question mark, vertical bar 7.
I also nest.
Yes, you can nest them. Yes, you can write 1 vertical bar, 8 vertical bar 3. Yes, because they
Would it be flattened like automatically?
does it flatten automatically? Yes, because I said the semantics of E1 vertical bar E2 is to yield all the values from E1 followed by all the values from E2. No more than that, right? So of course it has to flatten. Once I tell you that's the semantics. In fact, I'm sort of giving you a denotational semantics on the fly, in a way. Yeah, anyone else? Okay, so let's see. We can do nested choices, and this is just like a Haskell list comprehension with more than one binding, right? And as you might guess, here we choose x successively to be 1 and 2, and then we choose y to be successively 7 and 8, and the one to the right iterates more rapidly, so this is like a nested for loop. It's like for x equals 1 dot dot 2, do for y equals, do you get the idea? So it's just like nested for loop, just like Haskell list comprehension, should seem quite familiar, I hope. But at any moment, remember, x has type int and y has type int. They're not bound to multi-values, they're bound to single values. That helps reasoning, really, because it's what Tim described as a pointful style. Right. You're looking very puzzled, John. That's the mouse pointer. This is not a microphone.
No, I'm just imagining saying x becomes some choice, y becomes 1 dot dot x. That's perfectly okay.
Yes.
Right? And then you told us earlier that the order didn't matter, that we could swap those over. And I'm just wondering what that program would mean.
Yes. So if you write y is 1 dot dot x semicolon x equals 1 dot, then indeed you get into some quite tricky corners that Leonard and I have. And so Leonard and I spent a long time talking about this, and then we'd go and talk to Tim, and we'd say, Tim, what does this do? And he would say, and then we'd try to formalize it. So this has been the sort of Socratic dialogue that has played out. It's very entertaining, but I'm not going to do that now. Okay, so I will. But you are starting to get at why it is not trivial to even say what verse means, and why just saying let's ask Tim doesn't scale very well when you have 100 million programmers, because he is running $1 billion company at the time. It doesn't scale terribly well even now. Okay, all right, good. So conditionals. Tim covered this a little bit. Very old idea. Icon had this idea back in 1979. Right? Verse does not have a separate Boolean type, like almost all languages, including Haskell type, has. Instead, the scrutiny of a conditional, if it fails, that is, yields 0 values, we take the else branch. And if it succeeds, that is, yields 1 or more values, we take the then branch. Does that make sense? So it follows that if you want to say, if x is bigger than 20, what have we learnt about greater than? We've learnt that greater than must be a function that compares its arguments, and if x is not bigger than 20, it fails. That is, returns 0 results. If x is bigger than 20, what do you think it returns? What was that? All the elements bigger than 20? No. It could be. I mean, it could be a choice that we make, but we don't, right? If x is bigger than 20, it returns x. Right, so it's, and actually that is a bit cute. Have you seen mathematicians write, if 0 less than x less than 20, then blah, blah, blah? That actually works in verse, strangely. I'm going to let you work that out. This is not a new idea, but it's an example of just, once you've got something, like returning multiple values, you might as well use it, and we do. Okay, so now to your question about, sorry.
So if I have x equals 10 or 20 or 30,
yes,
and then I check if x is bigger than 20.
Yes, so you're saying, if you say x colon equals 1 or 2 or 3, and then you say if x is bigger than 3, well, remember, x is first bound to 1,
yes.
Then we get to the f.
Yes, but when you said that the greater than returns x,
yes,
does it return the entire sequence, or?
No. Remember, at any moment, x is bound to a single value.
Yes.
Right? So at any occurrence site of x, it's just a single value, right? Then we're going to go right back to the binding site of x and bind it to a new value, and then run everything. Just like Haskell list comprehensions.
Thank you.
Yeah. Okay, good question. Thank you. This is fun. Oh, good. Yes, over here. Run.
So if int of 3 returns 3 and x superior than 20 returns x, if it's superior, greater than 20, does it mean that greater than 20 isn't type?
Oh, does it mean that greater than 20 is a type? Yes, it is, actually. Greater than 20 is a type because it's a partial identity function, just like Tim said earlier. Good insight, yes. So greater than 20 is a great type, and it succeeds on all the values that are well bigger than 20. Yeah. So the type system is pretty rich. Between 0 and 10 is that 20, yes. Okay. So far, so good? Let's go. Now, back to your questions, right? So once you have these multiple values, I've stressed repeatedly that this x, the values that we're bound to are bound to one at a time. What if you want all the values? Well, you might want to collect them into a array or tuple. So 4, which Tim has already showed you, does that. It takes an argument that yields 0 or more values and returns the array of all of those values, the array or tuple of all of those values. And this is where order becomes super important because, of course, if you didn't know what order, it would become a non-deterministic language. Verse is very deterministic. So sequence is super important. We call it, the order tax. It has costs, but it has huge benefits as well. In functional logic languages, typically, this feature is left as a kind of afterthought because they're non-deterministic versus a deterministic functional logic language. Okay, so I've given some examples here, right, that I hope are fairly self-explanatory. So for of the, if it, the false question mark, the thing that returns nothing, well, it just returns an empty array. Okay? So vertical bar, as it were, goes from values to I beg your pardon, 4 goes from choices to a single value that is an array. Now, let's see. I've talked about all of this. And that tells you, by the way, except that choice, therefore, is not commutative, but it is associative. Yeah?
So all your examples shown so far have shown choices of the same type.
All my examples shown so far have shown choices of the same type, yes.
Could you have a choice of...
Can you have mixed things like, I don't know, one vertical bar, the string wombat? Yes. Then you have to say, remember we have to say what is a type, right? A type is just a partial identity function. You could have a type that was ints and strings. So yes. So the type system is pretty permissive, depending on what types you write. Yeah.
Other recursive bindings, so can be x equal choice of x and 1, for example. Do you have? Oh. Other recursive bindings can be x be equal choice of 1 and y, or 1 of x and x plus 1, or something like that.
X is a choice of 1 and x plus 1.
Yeah, for example.
Yes, okay, this is kind of like the question that John raised. I'm going to just dodge that because once we won't have time to go into the sort of darker corners of the semantics. But we have to answer these questions if we're to say this is what a verse program means. So I'm just going to ask you to talk to me afterwards about that. Okay. So I'm going to skip this. Now I want to get to functional logic, right? Because otherwise we're going to run out of time. So I've talked about choice, multiple values. Functional logic programming is the bit where we introduce what in Prolog you might call a logical variable, or we're going to call existentials. So here's the big picture. In Haskell or ML, and in all the things that I've shown you so far, when you bring a variable into scope, you give it its value. Right? So we say let x equal, that brings x into scope, and it gives it a value. Maybe a lazily evaluated value in Haskell, but nevertheless it has a single value that you know at the binding site. Now, and you do that in verse, but you can also not do that. You can bring x into scope without giving it a value. So here it is, I've just said x colon int. That just says x is an int. But I haven't told you what its value is. And later, perhaps somewhere far away, I say x is equal to 3. I constrain x to be 3. Does that make sense? So I'm going to call these variables that we bring into scope without giving them values existential variables, because of course that is what they are. So you can imagine I bring it into scope and separately I constrain it. And I hope you've already got the idea that since types are merely functions that fail on values outside their range, right? Even x colon int is short for, really, there exists an x, some x, and one of the constraints is that int applied to x succeeds, and another constraint is that x equals 3. So x colon int, you can sort of disaggregate even that. Okay? So I just want you to get the idea I want you to anchor in your mind is the idea of bringing a variable into scope without saying anything about what its value is yet. And so here's another example, which is a little bit more indirect. Here I'm bringing a pair into scope. So P here is going to be a pair. So I've given it a type, which is a tuple of an int and an int. And over in the red on the right, I've said, oh, and the first component of P is 3. And separately, I said the second component of P is 4. Right? So I gave it not its whole value. I didn't constrain its entire value. I just constrained part of its value. That's a pretty expressive thing to do. And you can, here's another way to say something similar. So here, look carefully at this. What am I doing? I'm bringing a new y into scope here and a new z into scope here. And then I'm saying I'm constraining P to be equal to the only equals inverse, just equals, P to be equal to a pair of 3 and y. And over here, I'm constraining the same P, that is this one, to be a pair of z and 4. So collectively, I've now nailed down P. It's the pair 3, 4, and I've nailed down x, and I've nailed down y. But I've done so in a rather, here and there kind of way. Okay? And these existential variables are very first class, right? I can pass them to functions. So that first function that I showed you, that is not some kind of magic built-in thing. This is the definition of first. Have a look carefully. So first here takes a P that is a tuple. It then says that P must be an XY pair where X and Y are also here existentials. And then it returns X, right? So, but when I call first here, right, there's a call to first, and I'm giving it P, which does not yet have a value. So this is a bit like passing var parameters in Pascal or something. I'm passing this as yet uninstantiated existential variable to first, which constrains it, right, to be a pair, and then returns the first component of the pair, which then gets constrained to be 3. Okay? All right. And I hope you're getting a little visceral sense of what functional logic programming is like. You can do all the prologue-y kind of things that you remember from your university courses about running functions backwards, right? Here's a swap function. I'm using pattern matching here that I haven't described in a formal way, but you can guess what it does. And I can either call swap on 3 and 4 and get back 4, 3, or here I can make an existential x and y, call swap on x and y, constrain the result to be 3 and 4, and that fixes x and y because it's sort of been through swap and worked backwards. Kind of cool, okay? Okay, so I think at this stage you get this thing. This is not Haskell, yes?
Doesn't this make it awfully horrible to reason about code?
Doesn't it make it awfully horrible to reason about?
Because I call a function,
yeah,
right? It might constrain its arguments.
Yeah.
And I have no idea.
What does it do? What does it do?
Can I tell?
So the first thing to do is we've got to have a way to explain to programmers what happens, right? So I'm giving you a very informal. In about 5 minutes' time, I'm going to give you a much more formal description about what happens that I hope will give you a way to say, okay, so now I see how I could reason about it, right? Then the grand experiment is, actually, when we get to the enterprise of writing large programs, is this a better way to write programs? And that is the grand experiment in which we are engaged, right? And it is a grand experiment. And just like, is functional programming a better way to write programs? I think so. But the proof that it is, we've been on a 40-year crusade. So our aim here is to take this slightly weird thing and kick it out of the lab and into the mainstream and see how it works.
Am I allowed to clarify what I'm driving at?
Yes.
What I'm driving at is, in Haskell, if I call a function, I know it doesn't have any side effects.
Yes.
It doesn't poke at anything I've done.
Yes.
But it gives me back something that I can touch. And here, I give my arguments to a function. It might poke at my arguments. Right? That might be fine, right? That might be what I want, but sometimes that's not what I want.
So when you say poke at the arguments, it might constrain them in some way and might fail if they are not equal So that's not, so I have, been giving you a sort of visceral, well, it's side effectsy, but you should really just think of it, if you didn't pass it 3, then it fails, right? So it's not poking at them, it's just checking whether they are in fact 3 and failing if not. And the business of the implementation is to work out, is there a solution for all these logical variables? So you shouldn't think of it quite so much as a side effect, even though it might be implemented that way. But you're right, that it does, just as functional programming requires you to rewire your brain, if you're used to writing C++, so functional logic programming requires you to rewire your brain a bit, and that's a lot of fun.
Yeah, it's fun.
Yeah,
It
but I think it's, tell me if I'm speaking out of turn, Timmy, here. I feel as if there is a big experiment going on here about, is this actually going to be a better way to write programs? But you should say.
Yeah, it's definitely an experiment. We're learning more about it every day. But there's a lot of principles coming out that make it more sane. One thing with that function example is a function always promises to map one value from its domain to one value of its range. And a function that doesn't do that is rejected by the verifier. So the really interesting here with functions, you don't have to worry about having crazy side effects and all of this other state. But if you write that function in a very certain way, then it could run in reverse. Or it could run bidirectionally. Like consider long division where you have a numerator and a denominator, and you're going to try to produce a quotient and remainder. Given any two of them, you could solve for the other. And if you write your function carefully enough, then you could actually make it run bidirectionally. But it's still a normal function. It's still checked like a normal programming language checks a normal function. So it doesn't get all crazy.
Only a little bit crazy. So, look, I'm going to, I do want to, we're going to run out of time shortly. I just want to show you rewrite rules, right? Because I want to show you how you can get a handle on what this language might mean before we go too much further. I just wanted to point out on this slide that when you come to, you might have been thinking that if I say if x equals 0, as I am here, right? So if x equals 0, I've said this equals business constrains x. Well, we don't want to set x to be 0 in a rather side effecty way. We want to look at x, right? So somehow without setting it, right? So inverse, lingo and other logic languages have this. X here we want to be a rigid variable inside the conditional, but flexible outside. So that's another little piece of intellectual complexity that we've got to be able to explain in some civilized way, and I'll show you how to do that. Okay. Now, let me just sort of backing up a bit. Tim has actually been thinking about this for about 2 decades. As well as building a billion-dollar company. I don't quite have time to do all this, I don't know. But he's having a lot of thinking. And then Leonard and I and some others, Kuhn Klassen, Ranjit Jalla, Guy Steele, and Stephanie Wyrick, is a sort of little Max-verse team here. And our job is to suck out of Tim's brain all of these ideas and try to make them into something that can be explained in a precise way. And so that's been a lot of fun, but we have found repeatedly that whenever we start a conversation with Tim, we start sucking on the spaghetti, we end up like this, like this. So I want to give you a sense for how we have started to make sense of the big plate of spaghetti. So here it is. It's quite common when you're doing programming language design to describe some kind of core language. You take a big surface language, you transliterate it into some core language, and you give a formal semantics to the core. So for functional programming, that would be the lambda calculus, and GHC has this compiler intermediate language called GHC's core language. It's very small, it's just the lambda calculus. We're going to do the same thing. So here it is for verse, right? This is from an ICFP paper, ICFP in September, coming up. And so the very fact that the whole syntax fits on, just a little bit of one slide should maybe help to reassure you that something intellectually okay going on here. I'm not going to go through all this because I want to talk a bit about how programs might execute, right? So how are we going to run a verse program? Well, one way of thinking of it is we're trying to find values for all those existential variables that makes all those equations true. right? Do you remember we said, exists a p, and the first of p is 3, and the second of p is... What value of p would make all of those equations hold? Right? So that's our sort of high-level story. As Tim said to me very early, it's all very simple, Simon. He said, you just solve the equations. Operationally then, we might be doing something like, unification and backtracking and failure and choice and who knows what. But that's not very easy. That means you have to, if you want programmers to think about how their programs work, that's not a very easy way to think about it because it involves a lot of concepts that aren't part of their world. So let's instead use a more familiar technology. Yes?
So if
Rado.
all variables are existential,
Yeah.
doesn't it in practice mean that execution might be slow?
Oh, if all variables are existential, doesn't that mean execution should be slow? I'm at the moment just going to settle for knowing what programs mean at all, right? And then, since most programs will be much more straightforward and won't involve weird control flow, we'll just compile the hell out of it, right? And for common patterns, we're going to compile them into, I don't know, C or something, C-like program. And when you do weird John Hughes-like data dependencies, then it's going to be slower. But just like, this is exactly the question that I was asked 40 years ago, this functional program, lambda calculus stuff, it'll never be fast enough, we need to use BCPL, right? I think functional programming has turned out to be fast enough, right? And I think this will too. But I'm still on to, how can you explain what programs mean? So here's what we do for Haskell. When we say to programmers, what does a Haskell program mean? We don't talk about stacks and heaps and pointers and thunk updates. We just say, you just rewrite your program. So here's here's a little example. Here's an expression, foo of 3 plus 2. We can rewrite that by inlining foo to a let, right? And then we can evaluate different parts of the 3 plus 2. So, or we can, here we can evaluate the 3 plus 2 to 5, and then we can inline foo, and then we can do the addition and so forth. So you get the idea, right? But the point about this thing is, there's many rewrites you could do at any time, but they all lead to the same value. And this isn't, of course, how GHC executes the program, but it's a solid model for programmers understanding what programs mean. So you can apply any rewrite rule anywhere in the code at any time, and you get an equivalent program. And the rewrite rules are directed so that if you keep executing them, you make progress towards a value. Right? The rewrite rules are confluent, so-called, because it doesn't matter what order you apply them in, you always, in the end, get to the same value. All right? This is actually not just good for programmers, it's good for compilers, because compilers do this kind of transformation all the time. It's maybe not so good for a final execution mechanism, but that's the business of the sort of back end of the compiler. Okay, so how are we to apply this kind of technology to verse? Well, here's an example. So I'm going to take my my example here to be this little one with x being a tuple, and it's constrained first to be equal to 2 comma y, where y is also an existential. I should have made y an existential here, and also z is here. Okay. So if I desugar that and put the existentials in explicitly, I get something like this. So the x is a variable, x is constrained to be, well, there is a y, such that 2y, and there is a z, such that the tuple z3, and I want x to be equal to those two tuples and finally return x. That's my program. How do I execute that program? Well, here's how. So let's see, the first thing I might do is I might float these existentials here out to the front. Maybe that's a valid program transformation, right? That takes an equal program to an equal program. Then I might, what shall I do? Substitute for an occurrence of x. So what have I done here? I've taken this x, that red x, I've replaced it with, 2 comma y. Why have I replaced it with 2 comma y? Because this first equation told me that x is equal to 2 comma y. Right? So if we treat the first equation as a bit like a let, we can say, well, let me replace this second x here with the 2 comma y from the first one. So here it is, 2 comma y equals z comma 3. That was easy, right? Now what can I do? Well, maybe I can decompose this equality, 2 comma y equals z comma 3. That can only be true if z is equal to 2 and y is equal to 3. Just decompose the pair, all right? And now what? Well, now maybe I can substitute for, where have I got to here? Let me go over here. I'm going to substitute for this occurrence of x. So there's a red occurrence of x. Here's an equation for x. So replace that red x with 2 comma y. And then, oh look, now I can replace that red y, that occurrence of y, but I know that y must be 3. So let me replace that red y with 3. And now all of these existentials here and bindings have become garbage, right, because the final result, 2, 3, doesn't need any of them, so I can just drop them. Okay? So, nothing up my sleeve, right? No backtracking, no unification. Well, of course, this is unification, really. Just rewrites. And I've just repeatedly applied rewrites, just as you would do with a Haskell program, to get to my final answer. And, yeah. So there isn't a separate heap somehow. I'm not updating unification variables in some auxiliary data structure somewhere. The heap is, in effect, reified in the term, right? All of these these guys, these equations here, if you look at them through squinty eyes, they look very like a heap, right? In which the variable on the left is like a heap address, and the thing on the right is like the value. And that's very much what John Launchbury's, semantics was like, and Areola and colleagues' paper called A Call-by-Need Lambda Calculus first showed us how to reify the heap into the term. That's what gave us this idea. Somebody had a question? Maybe not. Yeah.
In this example, it's very carefully constructed so that all the existentials are solved when you return a value.
Oh, is the example very carefully constructed so that all the existentials are solved when we return the value? Well, if they're not solved, I have to return the value wrapped in those existentials. And that happened already right at the top here, look. I had to float these existentials out, right? So if this guy still involves some of these existential variables, I'm going to have to float those existentials out into the surrounding context. Yeah, just rewriting. So, and I want to just do homage to Alexis's remark yesterday. The unsung hero of this talk is, again, rewrite semantics. And indeed, the rewrite rules, here, these are all of the rewrite rules, they're in the ICFP paper. They're written using precisely the technology, the very same technology that Alexis showed us yesterday for rewrite rules. And they mean that you can give, well, the semantics of at least this fragment of verse on a single page of A4 in an ICFP paper. So I think that's pretty cool. And I think it's also new. I don't think people have really done this before. We're also working hard on a denotational semantics, because I've been speaking so much about expressions denoting a sequence of values. We're working hard on that. And Stephanie is doing, and there's a whole lot more that I haven't told you about and that Tim alluded to, including effects on I/O and transactions and structs and classes. It's like, this is the plate. We've only got a bit of the spaghetti so far in our laps. But the thing I want you to really take away is we really are doing this, right? It's quite an ambitious project. We're taking a niche idea, because people have studied functional logic a lot, but it has never really escaped from the lab. And our mission is to take it out of the lab and kick it into the mainstream. And coming to give this talk is part of an attempt to do that. This is a very open project. It's not, we're going to, not only is the specification open, right, we're publishing at ICFP, but the implementation, when we are sufficiently proud of it to be willing to share it, we're planning open source implementation. So this is very open to collaboration from academics or from people in industry. There's, Tim said, there's a preliminary version of this language without most of the features that I've described that's already shipping, and it will successively grow over time. Good. So please let's have any more questions or observations. Yeah. You got a question? How do we know that a program terminates? Oh, well, of course. I mean, that's a pretty hard question, right? We know that's a hard question, right? So when you say, Tim here, correct me if I'm wrong, if you give an effect annotation that says this thing terminates, then the verifier will do its best, and if it fails to prove that it terminates, it'll say, I can't verify your program. So we can't do magic. We'll make it sort of successively better.
But I might add, static analysis can figure out for reasonable programs whether you produce the allowed number of values. Like at the top level of a program, you're required to produce exactly one value. And a static analysis can determine that pretty reasonably, right? So it should be like with all of this work done that it's only problems that really cause mathematical undecidability that would prevent the verifier from successfully type checking a program that would, in theory, terminate.
Right, but termination is one of those undecidable problems, right? We do know that we're not going to succeed.
Right, but the fact that you can't solve the general case doesn't mean that you can still type check any program you could type check in a normal language.
Yeah. Let's go. Mary. Yes. Oh, you got the microphone. Yeah, all right. Yeah, force majeure. Go.
Yeah, so in the beginning, Tim said that it's not a lazy language, but it is lenient. So I was wondering, how does that play here with the existential variables? Because in all your examples, you have finite tuples, but what happens if you have like an infinite collection and you don't want to do unnecessary work, so to speak? Like you have to know when, or what are the values that you actually need to assign in order to perform your calculation?
Are you talking about an infinite choice?
Yes, for example.
Let's see. Okay, so it's complicated. There are expressions that expand into choices, like 2 or 3 with the vertical bar. But there are also expressions that denotate or that stand for like an infinite set of values that are not produced by choice, like x colon int. It doesn't go off and produce all possible integers for you, right? When you see an expression like x colon int, that just waits for an integer to arrive. And so the language is very predictable about that. And infinite choices are not a problem. You can write functions in a way that construct them. But if you put them in a for loop, it will just run forever, like any other language.
Yeah, as it should Mary, yeah.
You talked about the verifier. What is the verifier? What does it do?
Well, what does it mean to verify a program?
Right, so and consider this as a language with basically 2 levels. You have a program on disk. You run it through the verifier both compiles the program to runtime form and checks that it is free of potentially reachable runtime errors. So the verifier, you can think of it, it's like a type checker, but it does more. It checks types, it also checks effects. But because the effects include any runtime error state other than divergence or explicit runtime errors that you cause, it results in a static verification of the program. And forces you to only write programs that are statically verifiable by it, right?
Let me make another attempt as well to see, and you can tell me if it means the same thing. If you declare a function with types for its argument and result, right, then you might hope that you might hope to verify that every caller would guarantee that the argument was in the type expected by the function, right? So the function will say as part of its domain, I expect an int. So you might imagine you apply int to the argument, and then you say, that call should never fail at runtime, should never fail, right? So the verifier's obligation is to prove that no execution path no call can cause that function to be applied to a non-int, okay?
I was kind of wondering what kind of technology sits underneath,
Oh, what kind of technology does that verification? Kuhn-Klassen. Who, for the rest of you, is one of Mary's close colleagues. That's the technology. And Ranjit Jala. I mean, that is what we're working on very actively. So it'll be something like we'll translate into first-order logic, or we'll invoke Z3, or we're sort of exploring that space. We don't really know for sure. But we have some pretty powerful technology applied. Yes, John, you've got the microphone.
Yes, so earlier on we saw negation in one of the examples, and I saw that and I wondered, is that negation as failure? Well, I guess that it is negation as failure, which can have some funny behaviors together with uninstantiated variables. I imagine that your distinction between rigid variables and, what were the non-rigid ones called? You had some distinction that meant that variables did not get instantiated as the result of tests, but you went over that rather quickly.
Yes.
I imagine it's a key part of ensuring that problems with negation as failure don't arise.
Yes, so you're talking about, I talked about that flexible and rigid thing, and then I said I'm going to sort of explain how that worked, in the rewrite rules, and I didn't really. So So take that for construct, and if has a construct that it's called one that works rather similarly. So how can I put this? When you do, when I do this substitution here, yes, I've taken an x equals something, and I've used it to replace an occurrence of x, right? Now, when I said if x equals 0, then what I cannot do is take that x equals 0 equation and use it to substitute for an x that occurs outside, right? So it's not really that it's rigid, it's just that I restrict the scope of the substitution of an equation. Here, this x equals 2y, I can use it to substitute anywhere in here, but I can't use it to substitute sort of outside an if scrutiny. Now I need to say, what does it mean to be outside an if scrutiny? And you should go to read the paper just to see what, but it's not very hard. But it's not actually a distinction about flexibility or rigidity in the rewrite rules, it's just how far out does the substitution rule reach? That's the key trick. The front row has been very dominant here, so what about, well, but you haven't had to ask a question yet, so
yes,
go.
So my question is, one thing is creating a language, other question is, another challenge is adopting it, right? So you have to convince the developers you should use it, and developers would have concern like, I'm interested in what are the third-party supports, etc. So how do you convince developers to use it? How do you convince developers to have third-party support, which they don't, unfortunately, right now?
Well, we're starting to jumpstart Verse bottom up. It's shipping right now as a scripting language in Fortnite, so there's a community of users who are doing the first experiments and building Fortnite gameplay that you can enjoy, and they're making money from it and building businesses. That's the first step. From there, we bring it into Unreal Engine, used by tens of thousands of developers, and release a permissively licensed open source implementation. Once it's at a good enough state. I think at that point it has the opportunity to go big and develop a community around it. But we want to really get the foundations in solid shape first, through this research effort, which is mostly academic collaborations.
But in some ways it's similar to, when Lambda, when Lambda was escaping from the lab into the world, I'm sure people would have said, professional software developers will never get this. But actually, of course you do. It's not rocket science, it's only Lambda. And so I think there's a similar process going on here. It'll take a while, and we'll see. But we'll see how valuable the expressiveness proves to be in practice.
Yeah, I think functional logic is fun. You can write more powerful conditionals and more powerful iteration, and over time, people become jealous of other languages having cool features that they miss. And over time, language designers realized they would like to implement the general solution rather than special cases. And so you look at Booleans and pattern matching in Haskell and other languages, a lot of these features are functional logic features that they've exposed in very ad hoc, limited ways. And at some point, it's going to become very attractive to start replacing the substrate of many other programming languages with functional logic, where it can play a simplifying and generalizing role.
Yeah, if I may ask a non-technical question, right? So, pardon my lack of understanding of game industry. How did the management go along with this rather avant-garde and pioneering language in the game industry? Maybe there's something you could shed some light on why this is applicable to the game industry.
Well,
you're looking at upper management.
Yeah.
Right, this is the boss.
It's you as a programming language designer. But Epic is a company that has always taken big technical risks to do new things. With this generation of technology, we pioneered micro-polygon geometry and real-time global illumination. Unreal Engine was the first with real-time 3D constructive solid geometry as a tool. It invented this new networking architecture that's used by everybody in the game industry now. And so we expect we have to carry the torch for progress in the industry because very, very few companies do nowadays.
Yeah, Epic is, as far as I know, the only company whose CEO spends 2 or 3 hours a week talking to British and Swedish computer scientists about denotational semantics.
And last question. All right, so I'm wondering why, I have some ideas, possibly why, but why I have array and choices, and how would they compose? Can I have choices of arrays, arrays of choices? And I guess as a bonus, can I have choices of choices?
Well, let's see. You can think of arrays and all of these other things as just simple values. An array, it's just a value. It's something that's frozen in time and isn't going to change, whereas choice represents sequenced value production, right? So it's like Haskell list comprehensions. You have a list. You have a list you started with and a list you're producing. You're iterating over one list, producing another. And inside the comprehension, there's all of this really interesting monad plumbing going on. In verse, the equivalent of that is just a bunch of choices producing values. And the choices can come from many sources. You can have the A vertical bar B operator, or X colon X's saying for every element X in this array X's. But they're always executed in sequence. And so there's always, the choices are always produced in a well-defined order, just like a Haskell list comprehension. And everything we talk about in verse can be translated into Haskell monads and vice versa. We just have what's really different here is a different translation from syntax to semantics. It gives you more flexibility in the plumbing.
Thank you.
But an array is a value, and a choice is not a value. So an array can contain arrays, which can contain arrays, but which can contain numbers. So it's values all the way down once you've got to an array. Choices are always at the outside, if you like. That's why I was repeatedly stressing variables are only bound to values, never bound to choices.